ever feel like you're just drowning in information? You know, like every single day there's this huge wave of articles, reports, data.
Oh, absolutely. It's overwhelming.
Right. And you just need to find the important stuff, the things that actually matter, without spending like hours digging through it all.
Well, that's exactly what we're diving into today. We're looking at how we can cut through that noise.
Okay, good. Because this deep dive is focused on that.
Yeah, we're exploring this really fascinating area of AI, looking at a language model called LLaMA2. It's from Meta AI.
LLaMA2, right. Heard of it.
And it seems to be making some real progress in how we understand and categorize documents, specifically in English. Our main source here is a research paper looking directly at that. Leveraging LLaMA2 for improved document classification in English.
Okay, so LLaMA2 sounds powerful, but maybe a bit abstract for some listeners. Let's make it concrete. What is document classification, really?
Sure. Think about, say, thousands of customer reviews coming in. Document classification is what automatically tags them positive, negative, maybe neutral. Ah, okay. Like sentiment analysis.
Exactly. Or, you know, when Netflix recommends shows you might like, that's based on categorizing content.
Yeah.
It's sorting documents, essentially.
Gotcha. Even finding that one specific email in a massive inbox.
Yep. Information retrieval often relies on this kind of automatic sorting. So our mission today really is to see how LLaMA2 is supposed to make this whole process, well, smarter, more insightful than maybe the older ways.
And maybe uncover some surprising things along the way.
Hopefully. Maybe a few aha moments.
Yeah.
Because this isn't just some niche techie thing anymore, right?
No, definitely not. It sounds technical, maybe document classification, but it impacts so much. You see it everywhere.
Totally. It's becoming fundamental in our data-heavy world. Think about identifying fake news or just improving how we access information in, say, universities, like Kachenko and Denisova highlighted.
Right. Or in businesses dealing with mountains of data, as Wang and others pointed out years ago.
Precisely. So making sense of text automatically is incredibly important now. Okay, so how did we used to do this? Before things like LLaMA2 came along.
Well, for a long time, it was honestly pretty basic. You might have someone manually creating rules.
Like if it says angry, mark it negative.
Exactly like that. Or using simpler statistics, just counting how often words appear. Some folks like Yao and his colleagues explored that back in 2005. Rule-based stuff, knowledge engineering.
But I imagine that hit a wall pretty fast with the explosion of digital text.
It really did. Those methods just couldn't scale, and they often missed the nuances of language. They were kind of brittle.
So what came next? How do we get smarter about it?
Well, the big shift was towards machine learning. Instead of writing explicit rules, we started training algorithms.
Letting the machine learn the patterns itself.
Right. Techniques like support vector machines or SVMs and k-nearest neighbors, which Corday and Mahender wrote about. You'd feed them lots of labeled examples.
Like this is a sports article. This is politics.
Exactly. And the algorithm learns to tell them apart. An SVM, for instance, tries to find the best dividing line between those categories.
Okay, that sounds like a big improvement.
It was. And then came deep learning, which took it another step further, inspired by the brain, using these complex networks.
CNNs, GNNs, I've seen those acronyms. Patharaju, Tambay, and Wang, Ding, and Han have papers on that, right?
Yeah, those models can learn even more intricate patterns automatically, directly from the text.
So from rules to basic stats to machine learning, then deep learning. Where do the big language models fit in? Things like BERT.
Ah, good question. So BERT and others like RoBERTa, even specialized versions like DocBERT for longer texts, these were another huge leap.
Gortiev wrote about BERT, Liu about RoBERTa, Adhikari on DocBERT.
Right. These are large-scale pre-trained language models. The key is pre-trained. They've been trained on just massive amounts of text data, like scraped from the internet.
So they have a much deeper understanding of language.
That's the idea. They capture complex relationships between words, context, subtleties that earlier models often missed. Galal and colleagues, and many et al., have pointed this out. They get the structure of language better.
Okay, so that sets the stage perfectly for LLaMA2. It's building on all of this history.
Exactly. LLaM2 uses a similar underlying architecture, the transformer mechanism, which was a breakthrough in itself. But it has its own specific design, including these things called attention mechanisms.
Attention mechanisms, what does that mean in practice?
Think about how you read a long document. You don't weigh every word equally, right? Your brain kind of zooms in on the important sentences, the key phrases to get the gist.
Yeah, you focus on the core message.
Attention mechanisms let the model do something similar computationally. It learns to assign different levels of importance or attention to different parts of the input text when it's making a decision, like classifying the document.
So it can better figure out what the document is really about.
That's the goal. To improve accuracy, definitely, but maybe also offer a bit more transparency, more insight into why it decided a document belongs in a certain category compared to just getting the answer.
Right, more than just a black box. So our deep dive today is unpacking how LLaMA 2, with these transformers and attention, tries to get past the limitations of even models like BERT and RoBERTa.
Precisely. How it aims for better accuracy and maybe better interpretability in document classification.
Okay, great setup. So let's get into the specifics of the study. They actually tested LLaMA 2 on this task.
They did. The paper we're focusing on, leveraging LLaMA2 for improved document classification in English, did exactly that. They used a specific data set.
What kind of data?
It's called WOS 5736. It's a collection of several thousand abstracts, summaries of academic papers, covers various scientific fields.
Okay, so scholarly text, what did they do with it?
First, they cleaned up the text, standard pre-processing stuff, then the key step. They used LLaMA2 to generate numerical representations for each abstract.
Like turning the words into numbers the computer can work with.
Sort of, yeah, but more sophisticated. It's like creating a dense vector, a kind of unique mathematical fingerprint for each document that captures its semantic meaning, according to LLaMA2.
Okay, these LLaMA2 fingerprints, then what?
Then they took these representations and fed them into more traditional machine learning algorithms, the classifiers, like SVM, random forest, KNN, the ones we mentioned earlier.
Ah, so it's a two-step process.
Yeah.
LLaMA 2 understands the text, creates the fingerprint, and then something like SVM does the actual sorting based on those fingerprints.
Exactly. They tested various combinations.
I don't know what happened. Did the LLaMA 2 approach work well?
It worked very well. The combination of LLaMA2 embeddings, those fingerprints, paired with the support vector machine SVM classifier, gave the best performance overall.
How good are we talking? Any specific numbers?
Yeah, they reported a weighted AUC-ROC score of 0.9945.
Okay, AUC-ROC. That basically measures how well the model can distinguish between the different classes, right? Closer to 1 is better.
Right. So 0.9945 is extremely good. It means it's very reliable at telling apart, say, a physics abstract from a chemistry abstract in that data set.
Wow. Any other metrics?
They also highlighted the weighted F1 score, which was Meadow 0.9306 for the LLaMA2 SVM combo.
F1 score. That balances precision and recall, like making sure it finds most of the right documents without grabbing too many wrong ones.
Exactly. It's a good measure of overall accuracy in classification tasks. And again, 0.93 is a very strong score.
Okay, those numbers sound genuinely impressive. But the crucial question is, how did it stack up against those other big models like BERT and RoBERTa?
That was a key comparison in the study. They ran BERT and RoBERTa through the same process, generate embeddings, then feed to SVM, etc.
Did LLaMA 2 pull ahead?
It did. While BERT and RoBERTa also performed very well, as expected, the LLaMA2-based models consistently either matched or slightly outperformed them, particularly on that weighted F1 score.
Slightly better F1.
Yeah.
What does that suggest?
It suggests that LLaMA2 might be slightly better at capturing those subtle textual features that really help differentiate between the categories accurately. It's finding those little clues that lead to fewer misclassifications.
Okay, so potentially a bit more accurate. What about the interpretability you mentioned earlier? Did LLaMA 2 offer more insight into why it was making classifications?
This is where it gets visually interesting. The researchers used a technique called TSNE.
TSNE. That's for visualization, right? Taking high-dimensional data, like those text fingerprints, and plotting it in 2D.
Exactly. They created these TSNE maps for the embeddings generated by LLaMA2, BERT, and RoBERTa. And the results were pretty clear.
What did they show?
The map for LLaMA2 showed much clearer, more distinct clusters of documents belonging to the same category. Imagine the dots representing abstracts on the LLaMA2 map, the physics dots were tightly clumped together, the chemistry dots were tightly clumped, and so on. Much more so than with BERT or RoBERTa.
Ah, so the different research areas were separated more cleanly in the LLaMA 2 representation.
Precisely. It suggests a LLaMA2's understanding of the documents leads to representations that better reflect the inherent structure and similarity between documents in the same field.
So it's not just getting the right answer, it's organizing the information in a more meaningful way internally,
Mm.
which we can then visualize. That sounds really useful.
It is. It suggests better feature extraction, a better grasp of what defines each category.
So thinking practically, what are the big takeaways? What does this improved classification mean for people?
Well, the implications are pretty significant for anyone dealing with large volumes of text researchers, businesses analyzing feedback, libraries, archives.
Anyone drowning in information, basically.
Pretty much. More accurate classification means finding what you need faster and more reliably. Better information retrieval. It could also enable deeper analysis, spotting trends or connections within the data that weren't obvious before.
Makes sense. Better tools mean better insights. Now, it sounds very promising, but usually there are caveats. Did the researchers mention any limitations?
Yes, absolutely. Like any study, it has boundaries. One key thing is the dataset itself, WOS 5736, is English academic abstracts.
So mostly formal scientific language.
Right. We don't know for sure how well these results would translate to, say, messy social media text or legal documents or completely different languages. That needs more testing.
Okay, dataset limitation. What else?
Computational cost. LLaMA2 is a large model. Running it, especially for generating those embeddings, requires significant computing resources. That could be a barrier for some potential users.
The classic big model problem. Needs hefty hardware.
Yep. Also, on interpretability, while the TS&E plots are suggestive, they noted that other methods, maybe involving specific prompting techniques, might give even clearer step-by-step explanations of the model's reasoning. It's interpretable, but perhaps not as much as some other approaches could be.
So room for improvement in explaining the why.
And one more thing. The LLaMA2 model they used wasn't specifically fine-tuned for any single scientific domain within the dataset. Tailoring it could potentially boost performance even further in specialized areas.
Ah, domain-specific tuning. Got it. And they acknowledge their funding source, too.
They did, yes. The Jia Xu Provincial University Philosophy and Social Science Research Fund supported this work.
Okay, so limitations noted. What about the future? Where does research go from here, based on these findings?
The paper itself suggests several interesting paths. One big one is tackling long document classification more effectively. Abstracts are short. Real-world documents can be much longer.
Right. How do these models handle thousands of words instead of hundreds?
That's a challenge. Another direction is integrating things like chain of thought prompting.
Chain of thought, like asking the model to explain its reasoning step by step as it classifies.
Kind of, yeah. The idea is to potentially improve both performance and that interpretability we talked about, make it show its work more explicitly.
That sounds promising. Anything else?
Developing more efficient, maybe smaller, lightweight architectures based on LLaMA2, that would help with the computational cost issue, make it more accessible.
Scalability and accessibility. Makes sense.
And of course, testing LLaMA2 and similar models on much more diverse data sets, different genres of text, different domains, and definitely different languages. They specifically mention exploring other LLMs, maybe like LLM-Informer, and looking at applications in Chinese, referencing work by Chen and others, and Zhang and Chen.
So broadening the scope significantly.
Exactly. Understand the full range of its capabilities and limitations.
Okay. So as we wrap up this deep dive, it leaves you thinking, doesn't it? Consider just the sheer volume of text generated every single day. Research papers, news, social media, emails. It's astronomical.
It really is mind-boggling.
And advancements like using LLaMA2 for document classification, they could fundamentally change how we interact with all that information, how we find it, how we understand it, how we use
And
it.
it really opens up possibilities.
So maybe think about that. What new avenues could this unlock for you? In your field, your work, even just your areas of interest. How might this ability to automatically understand and categorize text at scale continue to evolve?
And what new questions, maybe even ethical considerations, arise as these tools get more sophisticated? It's definitely something to keep an eye on.